Hi, in this video, we're going to go over some hints for WebAssign 16.1. So let's start with this first one. We have an automobile. It's got tires with this radius. It travels 6,500 kilometers before wearing them out. How many revolutions do the tires make? Neglecting any backing up. So basically, we need to just first up, we can't have it in kilometers. We need to change it into meters. So you're going to want to multiply by 1,000 to change it into meters. So do that first. But basically, that's going to end up being, well, there's two ways of kind of looking at this. One way would just be to take the distance that it goes and divide by the circumference of it. So divide by 2 pi r, because that will tell you how many times it has to go around. So that's probably the easiest way to do that, would be my recommendation. So the other way to do it would be to use x, where x is how far you've gone. The other way to do it would be to take x and use the theta r and solve for theta. So, and then take that theta and divide by 2 pi to get the revolutions. So that would be the other way to do it. Think about it. So either one would work. Up to you how you want to do it. Number 2, a truck with a radius of 0.385 meter radius tires travels at 42 meters per second. How many radians per second are the tires rotating? That's a pretty easy one. Just go ahead and use the V is equal to omega r, solve for omega, and that will tell you the radians per second. So for part A, you do that. To get it into RPMs, so basically you're going to take your, however many radians per second that you've just calculated, and and then I would do think about it in terms of the train track method. There are 2 pi radians in 1 revolution. There are, so of course you would have the number for part A there. And then I would take, there are 60 seconds in 1 minute, and that will get you 2 revolutions per minute. So that's how I would think about doing part B. So for part 3, it says the phonograph accelerates from rest. So that tells you your initial omega would be 0 to final omega, which, just take this, and I would do the reverse train track method to get it into radians per second. So, basically, again, so now you got revolutions per minute, and kind of just do the opposite to get it into radians per second. So, basically the above situation. But anyway, once you've done that, then that's going to give you your omega final. You get your time is given, and then you need to do alpha, find alpha. So I would recommend the Paul equation for that. And then to change it into revolutions per revolutions. Let's see here. So I would first solve for theta. So I might solve for theta using, let's see here, like the John equation would probably work pretty well. Right, you got everything you need, obviously, so that part would be 0, and that part would be 0. Solve for theta, and then take theta, divide it by 2 pi to turn it into revolutions. So that would be how I'd do part B. So number 4, with the aid of a string, a gyroscope is accelerating from 25 meters from rest to 25 radians per second. So this is even easier, right? Your omega naught would be 0. Your final omega is equal to exactly what it tells you, right? No, don't have to change anything. You got your time. What is the angular acceleration? Again, very similar to number 3. I would just go with the Paul equation on that one, and solve for omega. Part B, very similar process, to, same as 3B. So, okay. Number 5 is actually very tricky. It is a ton of steps. So this is probably what's, worth watching this video for just for this one. So for this one, I'm gonna take over some of this room up here. We got the spinning up part, which is the part where it accelerates, and the slowing down. For the spinning up part, you got to figure out what is the angular acceleration, what is the final velocity, and then you have to do basically, and then what is the angle. So you have like basically 3 things to kind of figure out. So, oh wait, hang on, we don't have to find the final velocity, but okay, so that's going to be our final velocity it's given, except that you're going to have to turn it into radians per second. So step 1 would be to find alpha. My suggestion would be similar to number 4. Use the Paul equation. You know what the final omega is. That's going to be this 5.2, but again, in revolutions per second. Your initial would be 0, plus, let's just do this. We'll write out the equation. Alpha t, so that's going to become, right, because your initial omega is 0. So that'll allow you to figure out alpha, and then once you have alpha, then you can figure out theta. So very similar to number 4. I would recommend probably using the John equation. Again, all of that would be 0, and solve for theta. So that's for the spinning up. For the slowing down, so let me just really quick, let's take this 52 or 5.2. So 5.2 revolutions. Oh, that's because it's revolutions per second. That's easy to change, right? 60. Oh, wait, hang on. Just got to change my 1 revolution is equal to 2 pi radians. So I just have to multiply by 2 pi. So that's really easy. I got my 5 point. Obviously, yours is going to be a different number. Pi. That's going to be 32.3, or sorry, 32.7. I'm just doing that, and that's going to be radians per second. So the reason that I did that, right, so that obviously would go here, 32.7. So the slowing down part, again, kind of the goal here is to find theta for spinning up, theta for slowing down, and then add them together. So for the slowing down, we got to basically do the same thing. So the first thing is find alpha. So we know that, so we'll do the same equation here, t. We know that our final velocity is 0 because it's slowing down to a stop. We know that our initial velocity was 32.7, and then alpha, and you're given the time, which was, in my case, 16.5. Obviously, it'll be different for you, but just so that you know kind of how to set that up. So then, right, figure out theta. We can say that that's 0. But you will have to have your omega 1/2 alpha t squared. So, right, you would have to have your 32.7, again, whatever yours is, and then your 16.5, whatever yours is. You got your alpha there, And again, the 16. Make sure you're using the time for the slowing down. But then you could find theta and then add the two thetas together. So, if I call this theta 1 and this theta 2, theta total would equal theta 1 plus theta 2. And then to get it into revolutions, you just have to do theta total divided by 2 pi equals, what the heck, why? Equals revolutions, right? So that would be your last step. So, all right. So next, looking at number 6 here, we have a kid is outside his home playing with a metal stick and hoop. He uses the stick to keep the hoop a radius of 45 centimeters rotating along the surface. At one point, the hoop coasts down the hill and picks up speed. So, let's see here. If the hoop starts from rest, so that tells us our initial omega would be 0, and reaches a linear speed of 8.5. Okay, so we can just take that omega is equal to v divided by r. That just came from, right, the v is equal to omega times by r. So I just rearrange that. And when we got our time, obviously. So figure out the angular acceleration. That would just be the Paul equation there. You, of course, have the initial omega, you got the final omega, and you have the time. So you got everything you need there. So let's see here. If the radius of the hoop were smaller, would that affect the angular how would that affect the angular acceleration of the hoop? Well, I mean, think about where r is, right? So let's assume, right, the linear speed, this, let's say this 8.15 is, that's going to stay the same. So if I made it a smaller r, then, right, I'm going to divide the velocity by a smaller number. That's going to make the omega bigger. If the omega is bigger, then my alpha would be bigger. And if we think about that, that kind of makes sense, right? If it's a smaller hoop, it's going to have to spin faster to ultimately end up going the same speed. So that's kind of the reasoning that you would want to think about as you try to answer that question. So, basically what's going to happen to the final speed there. All right. This one is the final part of it is very similar to number 5. So let's take a look at this one. So the initial part's a little bit different because we start out with basically, right, a kid, let's say this is the top view, kid on a merry-go-round, and it's asking what is the maximum speed before he slides off? Well, the force of friction is the force that keeps the kid on the merry-go-round, right? As the merry-go-round spins. And so the limit at which he's going to fall off is when your centripetal force, mv squared over r, is equal to your force of friction, right? So, or your maximum force of friction. So as long, if this part, the mv squared over r, is less, meaning your velocity is less than the mu normal force, then, right, he's going to stay on. But if it's equal, then that's going to give you the maximum amount. So you're going to have mv squared over r is going to be equal to mu mg. You can multiply the r over and square root it. So you're going to get that the velocity is equal to, well, actually, at this point, I'm going to go ahead and stop. So you could basically solve that for the velocity. That's going to tell him when he's going to fall off. So that's going to get you that one. When you go to figure out the maximum angular speed, just take that velocity you got and put it into the v equals r omega to change it into an omega. To get the angular acceleration, that's very similar to what we have been doing. Alpha t, again, you would know that your initial omega is 0. Your final omega is your answer to part B. And you have your time as 11 seconds. So you'd be able to figure out alpha. So then D is the part that's very similar to number 5. So if we think about what we got to do, right, the first thing we need to do is find theta for speeding up. So I would go ahead and use the John equation again, just like we did for number 5. Again, those two terms are going to be 0. So then we'll call that theta 1 again. The second thing you're going to do is find alpha for slowing down. So just like number 5, we know that part. So let's see here. You would know your final speed is going to be 0. Your initial speed is going to be your answer, right? It's going to be the answer to part B. Let's make that a little bit nicer here. Right, because it's when the kid slides off, then it starts slowing down. So your initial speed in slowing down would be the final speed for part B, or the answer to part B. So whatever that is. Plus alpha t, you should expect alpha to be negative, both in number 5 and in this one. Right, in my particular case, I had 30 seconds for slowing down, so make sure you're using the time for it to slow down. And then 3 would be find theta for slowing down, just like number 5. Again, I would just go ahead and use the John equation. So let's say that part's 0. Then you'd have your initial omega, which again is your answer to part B. Again, whatever the final velocity is, your alpha from that part. And then you got your t squared, right? So in my case was 30 squared. Your number is going to be slightly different. And then as before, add the two thetas together. And then to get your theta total. And again, since you're looking for evolutions, take the theta total and divide by 2 pi to get the number of revolutions, which will give you your answer. So, all right, hopefully that will help. I know this one was definitely kind of tricky, so thank you for watching.